This is the second video on current for the electricity topic for Physics A-Level. In this video we will be reviewing the key ideas from the first current video and then looking at some exam questions, working up to a grade A star with some work solutions. So the first thing I want you to do is to read through these 7 questions, just pause the video and see if you know the answers. You can either do it in your head or you can write it down on paper. As with all topics in Physics A-Level, you must understand the basics. So it's very, very difficult to get make any progress on exam questions, especially AA star, unless you know the fundamentals. So the first question, the definition of current, the rate of flow of charge per unit time. Better than saying the rate of flow of electrons, I would say the rate of flow of charge. The per unit time is optional. The units of charge should be straightforward. That's the Coulomb, capital C. The charge of one electron, you're not expected to know this, but you are expected to be able to find it in the data formula booklet and use it. So the elementary charge is 1.6 times 10 to the minus 19 coulombs. Why are metals good conductors of electricity? So we need to mention delocalized or free electrons. So they have more delocalized electrons than other materials, so there's charge which is able to flow when a voltage is applied. How do you connect an ammeter in a circuit? So we connect it in series. So the way we measure current is by measuring the amount of charge per unit time that flows past a certain point, which, as we will see, is very different to how we measure voltage. So you can see already we're making links between understanding how we measure current with an ammeter and how that relates to the definition of current. Kirchhoff's first law, we need to know this: the sum of current into a junction is equal to the sum of current out of a junction. And the rule for current in series, it's the same all the way around, which is related to Kirchhoff's first law. And similarly for parallel, even though it's a different rule, this is also Kirchhoff's first law. So current will split at a junction and then reform. So these are the key ideas on current that you must know before you're going to make any progress at all on answering the more complex questions. Right, so let's look at some exam questions. So have a read through these, pause the video. You might need 15 or 20 minutes to work through these. You could do this on a piece of scrap paper, you could do this digitally if you wanted to, but you really need to write something down, commit something to paper or to a screen. And when you're answering them, think about the significant figures, think about how you should present your information, think about the language used in the exam questions. And once you've had a good attempt at these, press play and you can listen to the solutions. Right, so question 1. So you're probably familiar with the idea that as the current flows, it transfers energy because of collisions. And then the material, the metal, will heat up. And if we increase the current, then the temperature will increase. But how we actually explain that for 3 marks is quite difficult. So we could refer to the rate of flow of electrons increases. So this is what we mean by current. So our definition of current was the rate of flow of charge. So if the current increases, then we're getting more electrons, more charge per second. That's very important. Now, we've only mentioned collisions very briefly. We will look at this in more detail when we look at resistance later on in this series of videos. So we know that resistance is related to collisions. So if we have more electrons flowing per second, then we're going to get more collisions. And we've got to be careful with language here. So if we just say more collisions, we might not get the mark. So more frequent collisions would be a better answer. And we need to say what is colliding with what. So the electrons are colliding with the ions in the metal. So if we understand that there's a transfer of energy when this happens, if there's more collisions per second happening, then we get a greater transfer of energy. So what does it say? The temperature goes up. Yeah. So the temperature is represented by the motion of particles. So the vibration will increase. Now this is a fairly typical example of a synoptic question. So this is drawing on ideas of resistance, which we haven't looked at yet, and also the idea of later on in the A-level course, you'll look at energy and kinetic energy and how that relates to particle motion. So probably a grade C on the surface, this question, but it could easily be a grade A or B question. Right, let's have a look at question 2. So terminology, command words, describe how the current varies. Normally, describe literally means state or write what you see, what is happening. Now, it's a little bit sneaky in this question because they do actually expect you to do a calculation, which is a little bit unusual. So if we have a look at our graph here, so we've got a charge measured in coulombs, we've got time measured in seconds. So we can see if the charge is 0, then the current must be 0 because there's no charge, there's no rate of change or rate of flow of charge. So between 0 and 1.6, that's that point there, the current is 0. So we haven't done any calculations there. We have needed an understanding of what we mean by current and the idea that if there's no charge flowing, then the current is 0. But we haven't done any calculations. We've just described what we see. Right, so then we get an increase. So quite often the increments on the scales are quite difficult to read. So there are 10 small blocks here for 2 seconds. So each block is 0.2. So this one up here is going to be, that's 2 blocks away. So that's at 1.6 as we figured out before. And this is a constant gradient. So calculation of gradient is a really key idea throughout physics A level. And we need to understand not only how to do it, but what the gradient represents. So if I was to work out the gradient anywhere on this this graph, I would be dividing the vertical by the horizontal. The vertical is charge, the horizontal is time. Charge divided by time is the current. So working out the gradient will give us the current. So all we need to do is to work out the gradient of this section here. So we go up to a total of 1.5, so 1.5 minus 0 divided by our 2 blocks here, 0.4, we should get 3.75. Okay, so we've got a constant gradient, so a constant current at that point. And then we have a fixed amount of charge. So even though the charge is non-zero, the rate of change of charge, the rate of flow of charge, will be 0. Alternatively, we could say the gradient is 0. So up to this point, up to 5 seconds, then we've got our 3 sections. Right, calculate, that's another command word, but we should be familiar with that one. What is the current when t is equal to 5.5? So once again, we're going to have to work out the gradient, but we can see here the gradient is not constant. We have a changing gradient. We start off, well, it's always negative. It starts off with a large value and then decreases to approaching 0. So the way we tackle problems like this is by drawing a tangent to the curve at that point. So there's a bit of estimation here, but as best you can, and obviously this will be very difficult to do without this in front of you. You might be able to estimate it on the screen. You could copy this into a piece of software and draw a triangle and take measurements, but it is quite difficult to do if it's not on paper. So we draw a line and then create a triangle and then work out the gradient of that triangle. So I got 1.7 vertical and 2.2 horizontal for the time. So we can work out the gradient. I got 0.77. Now, clearly, this is not necessarily subjective, but there's going to be room for error here. So a typical mark scheme would have a range of possible answers. So assuming the correct answer was 0.77, if that's the best answer, then plus or minus 0.2 would be acceptable. So if you got 0.57 all the way up to 0.97, you'd still get the marks. Okay. But there is a key point here about the exam tips. Learn the command words. That's very important. Right, question 3. So this is getting more difficult. We said this is probably a grade A question. Let's have a look at the answer and then we'll work our way through it. I think one of the challenges here, as very often with exam questions, is you might not know how to start. So the exam tip I'll give you here, if you're not sure how to start an answer, how to answer a question, then identify the topic, look in the formula booklet and write out some of the formulas. So it's talking about electrons, it's talking about current, so well, we could write down I equals Q over T. It's talking about, it says we've got a distance and we've got a speed, distance and speed, or maybe it's something to do with velocity. So if we've identified the two formula, then we can start to manipulate those formula and substitute values. So we're going to use this first formula, v equals s over t, so velocity is displacement over time. Make t the subject, t equals s over v. So what we're doing here, we've been given a distance of 0.35 and we've been given a speed of 3 times 10 to the 7. Typically electrons move incredibly quickly, especially if they're in a vacuum or a partial vacuum. So if I calculate the displacement divided by the velocity, I get a time. So that is the time it takes one electron to travel that distance. So even though it's a beam of electrons, we can imagine the journey of one electron. Okay, so then we move to I equals q over t. So we're trying to find the charge. Well, how do we know that? Well, again, almost process of elimination. We've been given the current, 5 times 10 to the minus 3, and we've just worked out the time it takes for that one electron to travel this distance. So I can work out the charge involved when a current of 5 10 to the minus 3 flows for this amount of time. So I multiply these two values together, and I get 5.83 times 10 to the minus 11 coulombs. Okay, so that's 2 marks. The third mark is we need to know how many electrons are needed to have this charge. Well, we mentioned this in the previous lesson. There is not a formula in the formula booklet. We just need to know or learn or work out that it's the total charge, which we've worked out here, divided by the elementary charge, which we know from the formula booklet, and we get our number here. And if I was to include the units here, it would be C divided by C. So the units in my answer are 0. I just want a number, and I would expect this to be a very large number because electrons are so tiny. So that sounds about right. If you got an answer of 10 to the minus 8 or just 200, then you think that's not enough electrons. It's probably incorrect. Right, the last question. So I would say this is an A-star question. It's a synoptic question. It's referring to moles, which we haven't studied yet. You may have studied this separately. You might have done this at GCSE. But the first thing we need to do is to work out the number of particles. So if I have 0.02 moles of anything, I know the Avogadro constant. We get this from the formula booklet. I can multiply these two together and work out the number of particles. Okay. And the particles we're referring to, the ones that can move, are the ions, in this case copper 2 plus ions. So normally, as we said in the first lesson, we talk about current being the flow of electrons, but it can be the flow of any charged particles. And in the electrolysis, here we've got positively charged particles. So if I know the total number of particles, I know the charge. If this was plus 1, then that would have a charge of positive 1.6 10 to the minus 19. It's 2 plus, so it's got a double the charge. So 2 times 1.6 10 to the minus 19. And that's the charge on an individual particle, so I can multiply that by the total number of particles to get the total charge in coulombs. That's very much the difficult bit, because now if we know the time and we know the charge, then we're right back to a relatively straightforward question. But it's, I suppose, getting this information is the difficult bit. So now I equals Q over T. We have our total charge. We need the total time in seconds, so 15 times 60, and I should get 4.28 amps. So 3 significant figures, sounds about right. Throughout all of these, I've shown all the working. I've written the formula, I've substituted the numbers, written the answer with the correct units. Okay, good. Hopefully that's been useful. Something I meant to mention last lesson, there should be a link to a quiz, a Kahoot quiz. It's just actually on the first lesson of the basic ideas, but if you find the link in the description below the video on YouTube, there should be a link there which can take you to a simple quiz on the key ideas from lesson 1 on current.